This film is a recording of a science show for primary schools presented by Dr. Alan Bruce of the School of Contemporary Sciences at the University of Abertay Dundee. It's been developed as a spin-out from the populous Tayside Space School and represents a series of science and in particular physics experiments for primary 6 and 7 pupils. It's designed to promote science in a fun and entertaining manner whilst using space and space travel as a means of introducing basic scientific principles and highlighting their importance in our everyday lives. The following presentation from the Space School was one of a series of 12 shows enjoyed by more than 800 pupils from across Dundee and Angus during 2012, and the University would like to thank the Institute of Physics in Scotland for providing funding to support the development and the delivery of these shows.
Okay, well, welcome along to this morning's session for the Space School. What we're going to be doing this morning is I'm going to be presenting a show that we call our Physics Fun in Space show. It's a show we've been taking out into the primary schools in and around Dundee and Angus. And the university and myself, I'm Alan Bruce, this is Ashok who's going to be helping me. We've set this up for you with support from a teacher at Dundee High School. And the money that's allowed us to do that has come from the Institute of Physics. So I'd like to thank the Institute of Physics for providing the funding for the particular show. I'm going to do a range of experiments with you today, some of them in physics, one or two in chemistry and biology as well, and I'm going to try and relate as many of them to space and space exploration as I possibly can. Okay? This world that we live in, this planet Earth that we stay in, the solar system that we exist in, all things are in one of three forms. They can be solid, my table's pretty solid, my head's pretty solid. They can be liquid, you can see liquids in some of these tubes that we're going to use later. What's the third thing that can be? Gases. Gases, that's right. And gases are a bit different. We know they're round about us, but we can't see them and we can't feel them. The air round about us is a mixture of gases. You know any of the gases that make up air?
Carbon dioxide.
Yeah, that's right. We breathe out carbon dioxide. What do we breathe in? Oxygen. That's right. Do you know what plants do? Yeah, they do the opposite. They take in carbon dioxide and they give out oxygen. So if it wasn't for the plants on this Earth, this planet of ours, we'd all be dead. They provide us with all of the oxygen that we need to breathe. Other planets in the solar system are totally different. They have different gases in their atmospheres. Our air is a mixture of different gases, oxygen, carbon dioxide, one or two others. Now the first experiments we're going to do, I'm going to put on my gloves because some of the chemicals I'm going to use here are quite corrosive. That means they burn your skin. So I need to be careful with what I'm doing. What we're going to do first is, you'll see here I've got two flasks. This first one is filled with a kind of grey coloured solution. Now you watch what happens if I shake it hard. Okay? Turns blue. Did I mix anything to make that happen? Yeah, I did. What did I mix? I mixed the gas that was in this part with the liquid. Can you see the froth, the bubbles in the top? So when I mix the gas and the liquid, it causes a chemical reaction, it causes it to change colour. This one here is called the traffic lights. It starts off yellow. If I shake it gently, it becomes red, orange first and then red. And if I shake it really fast, it becomes green. So like the traffic lights, it goes red, yellow, green. Yellow, red, green in this case. Right? Again, mixing the gas to cause the reaction. These next set of tubes, I'm simply going to mix the solutions and we'll see if we can produce any different colours. Right? So the first one produces purple. Any idea what the second one? Have a guess. What colour do you think?
Yellow.
Somebody said it there. Yellow. Right? That one gives yellow. This time?
Green.
No, blue this time. Can anybody tell me, if you mix all the colours together, what do you get? All the colours of the rainbow, mix them all together. No, a lot of people think that. Well, here's what you get. See if you're right. You mix all the colours of the rainbow together, you're right, you get white. White light. Here's a question for you. All of the energy on our Earth, our planet, comes from where? One source. The sun, that's right. So when the sun's white light comes into our atmosphere, and it's a rainy day like it is today, and it shines through that rain, what do you get produced? Rainbow. That is the white light from the sun being split in the rain droplets in the sky into all the colours of the rainbow. Red, orange, yellow, green, blue, indigo and violet. And I'm going to give these ashocks and hand these out to you. If you just hand them out to the front row, whoops, sorry. When you get them, have a look up at the lights. Because what these glasses do is they split the white light from the lights into all the colours of the rainbow. So Ashok will pass them to the front row, when you're finished, pass them back to the row behind. Okay? Inside these glasses, they're a bit like the 3D glasses that you get at the cinema, but they're different. They've got a prism in them. And that prism, it's like a piece of glass, it splits the light into all the colours of the rainbow. So when you look at white light, it breaks it into all the rainbow colours. So once you've seen them, if you pass them back to the row behind, I'm sure you've seen these things before. Yes? These things are called glow sticks. And if you're going camping or that, and it's dark in your tent at night, and you need some light, what you can do with these, inside here is a small tube with another chemical. So when you break it like that, you crack that tube and it releases the chemicals. The chemicals react together and they give you light. So the light shines through, so you can hang it up in your tent, it gives you enough light to read from. Or if you're older and you're going to discotheques, you can wave them around in the dark and wave them around your neck or around your wrist, and they come out all different colours. This is called fluorescence. It's basically energy being given off in the form of light by mixing chemicals together. So we mix these ones, we got colour. Mix these ones, we got colour. This time we mix chemicals to get light, energy given off. Have you ever seen the big satellites? In fact, these dishes on the roof look a bit like satellites. Big satellites, huge big silver mirrors in space. And light shines from them. Well, these silver mirrors have on their surface a thin layer of silver. And I'm going to try and make some of that. I've got here a flask, an empty flask. Is that correct? Not empty because gas, that's right. You're starting to think now. It's empty apart from that. There's gas inside, right? So I'm going to take that. I'm going to add these three chemicals to it. You tell me if you see any silver being produced. So we put the first one in. Nothing much happens. Put the second one in. You've got to make sure you're putting them in the right order. Second one goes in. Again, nothing much happens. Put the third one in. Something's happened, but it's not really like silver. It looks a bit more like the sort of dirty water you'd get in a muddy puddle on a winter's day. Right? If I was a magician and I was doing a trick, what would be the magic word that would make it happen? Yeah, abracadabra, that's right. I'm not a magician, I'm a scientist. So instead of shouting abracadabra, you're all going to shout, Ashok's going to count 1, 2, 3, you're going to shout science is fun. And I'm going to shake this like mad, because some experiments you need to put energy in to make them work. Right? So, if Ashok counts off 1, 2, 3, you shout science is fun.
Right. 1, 2, 3.
Science is fun!
Oh, it doesn't sound it from that.
Science is fun!
Hold on a second. I'm going to shake a lot harder, you're going to shout a lot louder, because I'm going to teachers tell me you can make a lot more noise than that, right? And wake yourselves up on a Saturday morning. Right, 1, 2, 3.
Science is fun!
That was better. Now, you see, I have to work really hard to get this experiment to work. What this does is it produces a thin layer of silver across the surface of the glass. It'll go black first, and then it'll turn and shine as silver. He said, hopefully. Right? Almost there. Right, if I lay it up there, see it now? Right. That's real silver. What happens is the chemicals react to produce a thin layer of silver, but it's only one molecule thick, very, very thin layer. And if you listen carefully, the liquids are still inside. And if I scraped off all the silver and took it to a jewellery shop, they wouldn't give me enough money back to buy the chemicals, unfortunately. So I'm never going to make my fortune. It's never going to go solid silver. But that's real silver, and that's how they make the finishes on these big satellites. Okay. This next experiment, I've got 3 solutions. Again, put them in the beaker, see what reaction takes place. Now, see the colour change that we get here doesn't usually happen immediately. I'm going to tell it to go blue. Oh, there you go. Now listen to me. See if you can make it go clear again. Think. Concentrate. Brain power that makes it happen. Alright, concentrate really, really hard and see if we can all make it go clear. I'll get back to being clear. Come on. Come on. Clear. Get back to being clear. Almost there. There you go. Now I want it to go blue. Get back to being blue. Come on, hurry up. Get back to being blue. Come on. Get back to being blue though. I don't want it clear. I want it blue. Give it a little swirl. Mix it up a little bit. Well, there we go. See if you make it go clear again. Somebody out there is not concentrating out. Come on, get back to being clear. There you go. Clear. Blue. Blue, come on. Blue. Hurry up. Blue. If it goes yellow, I'll be surprised. Right? This is what we call an oscillating reaction. It goes backwards, forwards, blue, clear, blue, clear. What happens is it absorbs oxygen from the air, and that causes a chemical reaction. And then the oxygen gradually leaves the solution, and that causes it to go clear. And then it absorbs some more. So it goes backwards and forwards, and then it's going clear again. It'll take it about half an hour to do that. And can anybody tell me, we talked about gases earlier, what gas makes up the biggest part of our atmosphere? It's not oxygen, it's not carbon dioxide. Do you know any other gases? Nitrogen, that's right. Nitrogen gas makes up about 80% of our atmosphere. Now if you take nitrogen and you change its temperature, you can change its form from solids to liquids or liquid to gas. Tell me, what happens to water on a cold winter's morning? It goes from being a liquid to a solid. And if you boil it in a kettle, got a kettle down here at the bottom, if you boil it in a kettle, what happens to it? It becomes a vapour and a gas that goes up into the atmosphere. So water can be solid, liquid or gas depending on temperature. Nitrogen is the same. So if you take nitrogen, you can't take it down just to freezing temperature for water, you have to take it down, right the way down to minus 196 degrees. Inside here I've got some liquid nitrogen. Nitrogen that's been taken down to that very cold temperature. Minus 196 is much colder than the North Pole, much colder than the South Pole. Much colder than your freeze box in your refrigerator at home. This stuff is very, very cold in here, therefore. Can you see the ice on the top of the tin? Right? What I'm going to do is I'm going to put this flour into the liquid nitrogen. What do you think will happen to it? It will freeze as quickly as that. What will happen to the nitrogen, however? Sorry? Nothing. Well, you wait and see. Now, before I do this, I've got to be very careful because it's dangerous stuff. And I'm going to put this glove on and I'm going to put this big mask on. And I'll actually bring it along to this part of the table so that you can see it a little bit more easily. Here. See it okay from there, everybody? Right? So, when I put the flour into liquid nitrogen, the flour is going to freeze. You watch what happens to the liquid nitrogen. It's going to warm up. And as it warms up, what will happen? When it's a liquid just now, it'll turn into a? No. Gas. You watch, right? Put the flour in. You see the gas coming off? And in a matter of seconds, the flours are frozen. You listen carefully. They're just like, that's exactly right, they're just like glass. They're frozen solid, and if I break the tips off, you can see they break off so easily because they're frozen solid. In a matter of seconds, they become frozen. And the gas that you saw coming out was because the liquid nitrogen heats up and becomes a gas. What do you think will happen if I put the balloon down into it?
It'll pop.
Hands up, who think it'll pop? Right, you watch that. What happens? Hold this my tongue, so you don't want my fingers in liquid nitrogen. I don't want my fingers dropping off like the heads of these flowers just did. Right? You put it down into liquid nitrogen, it's not popping, what's happening?
It's sucking out the air.
Well, you're not quite right there. It's not sucking the air out of it, it's cooling it down very quickly, and the gas that's inside the balloon gets cooled down, goes from being a gas, becomes a solid. And the solid doesn't fill the same space. So the gas is not coming out of the balloon, it's still staying inside, but it's being converted into a solid. And because the solid doesn't fill the same space, the balloon shrinks. So what will happen when I lift it back out? Reinflate? Well, it'll be frozen, yeah, but as it heats up, start to reinflate. Now you watch this, right? Now this is the nearest I get to magic in this show. So if we lift the balloon back out, and let it warm up slowly. Right? Turns into a kind of alien dog whose tail's not inflating for some reason. Right? Hands up, who thinks a cheese? The one you saw me putting in there is actually still in there. If this one turns into a blue dog, it really is magic. Right? Right, hold it. On up you come. Inflate, hurry up. Good, all the way back up. So I had hidden that one in the liquid nitrogen earlier, before the show. So it's like a sheet. Now that's liquid nitrogen. Tell me, have any of you ever had a doctor or a nurse put liquid nitrogen on your skin? Yeah? What do they use it for? Verruca, that's right. Verrucas are warts. They spray a tiny little amount of liquid nitrogen onto the surface of your wart or your verruca, and that kills the virus that's inside your skin that's causing the warts. It's a tiny little amount they spray on us. If they were using a lot more, it would burn all your skin, be very, very dangerous. Right, we mentioned earlier carbon dioxide. We breathe in oxygen, we breathe out carbon dioxide. If you take carbon dioxide down in temperature, it goes from being a gas, it doesn't become a liquid like nitrogen, lift this out from it, it becomes a solid. And they call it dry ice. And it looks just like ice. I've got a double it here. See it? I hold some up there, see it with my hand, it just looks just like ice. And you see already as it heats up, it starts to become a gas again. Now I need a couple of helpers for this. Your hand was up first, I'll take the boy with the second row up. Yep, you want to come out? Yep. It's easier if you come out and round this side and if you come out and round that very end. I'll explain to you what we're going to do. Don't worry, just put it back, just anyway. Right, on you come. What's your name? Should be able to see on the sheet. Sean and Ishmael, right? Come in, you come. Right, I'll tell you what we're going to do. Right. Okay, what we've got is two little containers. We're going to put a small amount of dry ice into them. Like that. And Sean and Ishmael are going to hold them in their hands. If they hold your hand, this one, hold it that way, scrunch it up like that, hold it there, point it that way. Right, oh, sorry, before we do it, we've almost forgot to get you to put your both safety glasses on. Nice to show. Right, so hold it in your hand, tilt that way so it's against the palm of your hand. Right? See it here, your hand will get really cold, but don't get worried, it won't do any harm. I've not seen anybody's hand drop off yet. Right? Have either of you got blood in your body? Yeah? Yeah? It's not cold. Not very warm-hearted today.
Have your breakfast this morning?
It's okay, well, yeah, no. I think I should probably put a wee bit more in. I just want to sit down a little bit. Whoa! Right, hold that way. Hold it that way. Yeah. reacting as quick as it should do this morning. Just run the man out. Why does the lid pop off? You saw the one that fell out.
Because air flows off and it's a bit like a carbon fiber.
Well, what happens is the carbon dioxide goes from being a solid, as it heats up it becomes a gas, and as the gas tries to escape, there's no way for it to go. So what happens is the pressure builds up, and when the pressure builds up, the only place it can go is to push the lid off. It's the same as a champagne cork out of a bottle. You ever seen, champagne, shake up the bottle, the gases build up inside, and the only thing it can do is to pop the lid off the bottle, push the cork out the bottom. That's why it sprays everywhere after that. Right, I'm going to leave that. Whoa! There we go. Took a while, but it got there eventually. Right? Okay, thank you. That's your seat back here. Right. I'm going to take some of the carbon dioxide and put it into this beaker of water. You see, immediately it starts to heat up and produce a gas. What I'm going to try and do is to produce a soap bubble over the surface of the basin, the bowl. So, rub some soap on there. Oh, nearly. Right? So what happens now is we've got a thin film of soap. Oh, it's burst. A thin film of soap over the surface of the bowl. So the gas can't escape. So it pushes the soap up and gradually it'll get bigger and bigger because the gas can't escape. A bit like the container. Now you watch what happens if it gets a bit bigger. I'll try and blow it from about here. Watch it. It's like jelly or somebody's brain.
Why does your brain look like that?
Because it comes to jelly. Right, see it wobbling backwards and forwards.
It's going to come up from jelly.
I'll leave it sitting there and see how long it takes for it to burst.
It's going to burst.
Eventually the pressure will get too much and the film of soap can't control it and it will burst and it will release the gas. If I blow it too hard, maybe. Oh, that bit. Right. Now, let's take these gloves off. Right, in here, I've got two balloons. Right? A blue one and a white one. You watch what happens if I let them go. Right? The white one goes down the way, and the blue one goes up the way. Why? Right, this one here I blew up. So if I breathe out, it's probably a mixture of oxygen and carbon dioxide, mainly carbon dioxide. And remember we saw over here, the carbon dioxide doesn't float away up, it just flows over the sides of the bowl. Carbon dioxide is a very heavy gas, right? So that one that's full with carbon dioxide is heavier than air, so it floats down the way, it's less dense. This one, you're right, is full of helium. And helium is lighter than air, so instead of flowing down the way, it floats up the way. Now I can catch it before it hits the top of that ceiling. Right, because it'll just go right to the ceiling. Now, before I do this next trick, I must explain to you, you should never try this yourself. And if you see your brother or dad or uncle or that doing it, you should never tell them to do it. I know that this balloon's got pure helium in it, because I filled up from a container this morning before you arrived. If you buy balloons down the street in the shops, they have a mixture of gases. Helium's one of them, but they also contain other gases which aren't too good for you. Right? So you should never breathe this. And I know what I'm doing because I've done this loads of times. So what we're going to do, I'm going to get Ashok to cut. Oh, that was my dog bursting. Right? I'm going to suck in a little bit of this helium.
You see anything any different to my dog? Why are you looking at me like that? But look like that. Look at all. Why are you laughing now? Now my voice suddenly changed to do that. I made a joke of Disneyland using the voiceover for Donald Duck to make it out or something. Why is my voice, my big manly voice, suddenly be up here?
with helium?
Last time, that's enough. You can only take in so much helium. Gradually, hopefully my voice will come back to normal. Right? Yeah, it's just about back. Well, not quite. It's getting there though. It's coming back to normal. Right? When you breathe in helium, in your throat, when you talk, sound is an energy wave. And it moves through the air. So as I talk, it comes out my mouth and it moves as an energy wave through the air to your ear. You hear me? Normally, before it leaves my body, it goes through this thing here. It's called your larynx or your voice box. Normally that's filled with carbon dioxide or air or a bit of a mixture. When I suck in the helium, this is now full of helium, my larynx. And helium, remember, we saw it's a less dense gas. The balloon floated away up, remember? So the sound wave travels faster through helium. Because it travels faster, it makes it sound as if it's way high pitched with that. And many of you believe in aliens. When you're doing the space school, you've got to believe in aliens. Everybody believes in aliens, right? If aliens exist, and we don't know obviously if aliens exist on some outer planet, some other solar system, if they do exist, they might talk like that. Because on their planet, there'll not be the same mixture of oxygen and carbon dioxide that we have. There might be a helium as an atmosphere on their planet. It's not likely this helium would drift away from the planet, but there'll be other gases. So they won't sound like us, they will sound totally different. And that's quite an interesting thought. Have you ever taped your own voice and then listened to it back again?
Yeah.
It doesn't sound like you, does it? It's a really strange thing that we hear ourselves differently from the way that everybody else hears us. And that's really weird. You think, oh, I sound just like that. But you don't, you sound a bit different. The reason for that is when I talk, some sound comes out my mouth and in my ear. But some travels up inside my head to the back of my eardrum. And I hear a bit of a mixture of the two. You only hear what comes out of my mouth. So it's interesting, it's odd. Everybody hears us differently from the way that we think we sound. I keep telling my wife I'm a really good singer, but she doesn't believe me. That has nothing to do with my voice. Right? What we've just looked at is the density of gases. I'm now moving on to the density of liquids. Two tubes here filled with these. Sprite and Diet Sprite, or Sprite Zero it's called. Right? I'm going to drop one of these little just pieces of carrots into these tubes and you watch what happens. You're going to tell me which one of these has got Sprite in it and which one's got Diet Sprite or Sprite Zero. Right?
I can tell.
Hold on. A second. Oh. There we go. Which one's which? Floats in one, sinks in the other one. It'll gradually come back to the top because of the gas, but it goes way, way down.
It sinks into zero.
You're exactly right. Why? What's in the other one that stops it from sinking?
Isn't it like gases?
No, it's not the gas. They've both got bubbles. You see the bubbles of gas. We've brought this one back to the surface. I'll try it once again. You see, it sinks so far, and then it builds up gas round about it, which brings it back to the top. The one that stays on the top is obviously more dense. What is it that's in it that makes it more dense? Now this is the one that's less dense, the Sprite Zero. It's that one with that one, and it's this one with this one. What is it? What's the difference between Sprite and Sprite Zero? Go at the back.
It's a sugar.
Sugar, that's exactly what it is. One can of Sprite contains about 7 teaspoonfuls of sugar. And sugar makes the liquid thicker. You can't see it, it looks just the same, but it's actually thicker, it's more dense. And that's why this is able to float on the surface, whereas the other one, you drop it in, sinks away down initially, before it eventually comes back to the surface. That's density of liquids. And it's the same if there are planets with water out there. We don't know if there are, but if there are, maybe different liquids with different densities. Okay? Right, moving on to this lot here. Did we put that together? Right, this one here is a plastic bottle with a balloon inside it. There is also, you can't see it, but I cut a small hole in the bottom of the bottle. If I cover that hole with my finger, right, and try to blow up the balloon, you can see that no matter how hard I blow, I can't blow up the balloon. The reason I can't is when I blow up the balloon, inside this bottle there's already lots of air. Oh, well done, Usher. There's lots of air. And that pressure from that air stops the balloon from getting inflated. If I lift my finger off the hole when I do it, See, I can blow up the balloon quite easily. And that balloon is a bit like your lungs. Inside your chest, as you breathe in, your lungs expand. We breathe out, it goes down again. Watch what happens, however, if I blow the air out, it forces all the air out the hole that's inside the bottle, and then cover the hole with my fingers. The balloon stays inflated. Even though it's open to the outside, it still stays up. That looks a bit odd, doesn't it? Because you think the air will just come back out. The reason it doesn't come back out is there is no air inside the bottle forcing it back out. No pressure on the inside. If I let go of my finger though, you watch what happens. It inflates right away because the air gets in the hole, forces the air out of that. That's pressure, different pressures. This next one's exactly the same. I'm going to use some of this boiling water. A bucket here just to get rid of it into. I'm going to pour hot water into the bottle and immediately put the top on. Right? Pour the water in, boiling hot water, fill it up, I'll fill it, pour it out, and then immediately put the lid on. You watch what happens to it. Without me doing anything to it, you hear it? It's getting compressed, it's shrinking in. The reason is when you put hot water in, it forces the air out of the bottle, tighten on the lid, there's no air inside, but there is lots of air on the outside, you hear it? It's pressurising, that's pressure, air pressure. We're going to do the same test, but this time with a glass, this is a boiled egg. Right? So, pour it in here. Pour it out, put the egg on, now you watch what happens to the egg. Without me touching it. Doing it. Yeah, we're getting there, I think. Without me touching it, he said, come on, get there. Still getting there. Keep watching it, it's going to happen. He said. There we go. And it goes. Looks like magic, doesn't it? The reason it happens, it's stuck halfway, I think. The reason it goes in like that is because of air pressure. Oh, there it goes. When I put the hot water into the flask, all the air comes out. The heat of the hot water forces the air out. I then set the egg on top. There is no air inside the flask, there's loads of air outside, and that air forces down through. Right? Have you ever seen on the TV and films of that when people are in an aeroplane and there's an accident happens and one of the windows gets smashed or the door gets blown off? What happens to the people on the airplane? Same as what happened to the egg. They get sucked out, don't they? The reason for that is inside an aeroplane, the aeroplane, remember, goes up into the atmosphere, and the further up into the atmosphere you go, the pressure is less. Right? But they artificially maintain the pressure inside what they call the fuselage, inside the cabin of the aeroplane. So everybody's sitting quite comfortable because the air pressure is maintained and you can breathe quite easily. If an accident happens and a window gets broken, however, all the air pressure is on the inside of the plane and none on the outside. So the same way as happened to the egg, people will get forced out through the hole, they get sucked out. So it's very, very important in space to know what pressure is. That's why the astronauts have big pressurized suits, supplying them with air internally. This device here, I need two people to come and give me a hand with this. Your hand is up first. In fact, both boys there. Do you just want to come out? These things are called Magdeburg hemispheres. They're just rubber suckers. Right? Stick them together, pull them apart. Right? So, what's your name? Josh. Hold that. Put your 2 fingers through like that, Josh. You strong, Josh? Yep, you look quite strong. Come around this side. Your name is? Andrew. Andrew, right? You do the same. Right, you look quite strong. We're going to find out who's the strongest here, or if either of them are strong enough. Put the suckers together, and, oh, sorry. Yeah. Push them together, tight. Right, pull them apart. Come on, push some muscle in. Come on, pull them apart. Whoa! Are you okay? Sorry. You have got muscles, guys, because nobody usually is able to pull them apart. Just wait a second. So, when we have the two of them together like that, when you push them together, you force out all the air between the two pieces of rubber. And it's very, very difficult. You saw how difficult the boys had to pull it apart. Right, this time, be careful, boys, so you don't fall backwards. Do the same again. Don't pull hard. What I'm going to do, get ready to pull, is, no, don't pull hard. I'm just going to open the edge a very little bit, like that. See how easy they come apart? Right? So we put them together, push out all the air, but if you open the edge, let the air in, you don't even need to pull them, they just fall apart. Because the air gets between the two rubber suckers and they just come apart. Okay, thanks boys. Round of applause for my helpers here. These things are very important if you're trying to climb up something that is a very flush finish, very shiny finish, because these things will stick it. You've seen some of the films. Move it for climbing up things. This chamber here, we are going to create a vacuum. Now a vacuum is when there is no air at all. You suck the air out. Now there are very few places on Earth where you have a true vacuum, a real vacuum. In space there are one or two situations where you can have no air at all. We have to create a vacuum artificially. We've got a pump here. So I've pressed on the pump, you listen to here. It's going to suck all the air out of this chamber through that hole. Right? This one's called the Marshmallow Man. You see my Marshmallow Man here. Right? What I'm going to do is I'm going to put him in the chamber. Can you see him okay? You watch what happens when I press on the pump. The pump is sucking the air out of the chamber. You watch what happens to the Marshmallow Man. He's been pumping iron. He's been doing his exercises. The size that he is now. Right? You watch, however, what happens if I switch this off and take off the tube and release the vacuum. Now he actually shrinks back to a smaller size than he was before. Why did that happen? Why does he suddenly swell way up?
Is it because it gets sort of like it's like.
Well, when you draw the vacuum,
Yeah.
inside marshmallow is one of these horrible substances. It's really gooey and sticky, and it's light. They're very light marshmallows because there's a lot of air trapped inside the gooey, sugary solution. Right? When you draw a vacuum, the vacuum tries to suck out all the air from this chamber, and it also tries to suck out the air from inside the marshmallow. Some of it escapes, but most of it can't escape because of the gooiness of it. But it still tries to escape, and as it tries to escape, it swells up, makes the marshmallows become very, very large. When you release the pressure, however, it shrinks way back down, even smaller than the normal size it started, because you have lost some of the air from within it. Now, I'm going to do a similar sort of thing with shaving foam, right? So if we put some shaving foam in the middle here, right? And I'm going to put some of this red dye on here just to make it more effective. You'll see it. This is to represent blood. Right? Put the chamber together. You watch what happens when we draw the vacuum again. Right? Same as before. Not this floor this time probably, but it's slack gradually coming up there. Maybe not got a connection for my vacuum. It's a bit like lava, yeah, it's tapered going underneath there. You start to go now, a bit more impressively. It swells all the way up. Not quite go to the top, I don't think, because the bubbles will start to burst as it gets further up, as the air bursts free from it. You watch, however, what happens if I quickly release the vacuum. Right, can you see that? Can you see what's left? That's what would happen to an astronaut in space if suddenly a suit was released. The pressurized suits that they have. That's what would be remaining. Right? The reason being, inside our body, we have lots of oxygen. We breathe it all the time. So inside the cells of your body, you have lots of oxygen, which, if the pressure is maintained, fine, no problem. If the pressure is suddenly changed rapidly, like I did by releasing that, that's the outcome. Right? Quite catastrophic for anyone. I'm going to get Ashok to stand there, put this on his head. Alright, stand still. This thing is called an earzuka. Right? All it is a big circular device, and it's got a piece of plastic and a rubber band inside. So I can pull this membrane back away and release it. So I'm going to stand here, see how good my aim is. Right? I can shoot that from Ashok's head without going across and touching it. What happens when you draw this back and release it, you can't see it, but an amount of pressurized air, a band of pressurized air, moves through the air and knocks the thing off the top of Ashok's head. Right? Lots of things in our everyday life rely on air pressure. Everything from lifts in building, the brakes in your car, doors, a lot of them are air operated. Pneumatics we call them, air pressure. Think about the space shuttle when it fires off from Earth. They burn up lots of fuel, that fuel is forced down the way, creates a jet of air to force the thing up and leave right out of our atmosphere. This one here is called balloon hover. This is just a plastic disc with a small hole in the middle. If I put it down there and try to move it, you see it sticks to the desk. It doesn't move very easily. The reason it doesn't move is there is what we call friction between the plastic and the surface of the balloon. If I blow the balloon up, however, this way. If I blow this balloon up, then put this on the top, you watch how easily it now moves. It's almost moving on its own, look. That's exactly the same principle. Air hockey, the bubbles of air come up the way. This one, the bubbles of air are going down the way. And it's lifting it up off the surface so that it can float around. But air hockey, air hockey is exactly the same. The air comes up, lifts the puck up so that you can knock it around and it moves really fast and easily. Can anybody tell me any other device that uses that for travelling around in?
No, hovercraft.
That's the one I was looking for, hovercraft. Hovercraft pushes air pressure down the way, lifts the machine up so it can travel across land or across water. Hovercraft uses air pressure. Right, single nail stuck in a block of plasticine, and what I've got here are 13 other nails. Who thinks I can build them all on the top of that one? One man's got confidence. Well, we'll try one first. Right, put one on there. Struggle even with one. But you watch it, you know how to do it. Put one nail down, you build the rest across it, from side to side. One nail from each side, all the way down, the central nail, until you've got one nail. Oh, this nail is also not flat, it's level. When you're left with one final nail, what you do with it is you put it across the top of them, the other way around. And then if you've got a steady hand, I'm convinced I have, you lift it all up like this, lift it across to here, and then if you're lucky, sit them all on the top. Right? So you can balance them all. They're not glued, they're just loose nails. That's how, have you seen roofs with a peak on them in buildings? That's how they build the wood joists, the trusses together in the roof. And it gives the roof maximum strength. That's why your roof doesn't blow away in a winter's day when it's in a howling gale. So it's all about the engineering principle. These things are called poppers. I'm sure you've seen them before. All you do is turn them outside in. Now by turning them outside in like that, they're made of rubber or plastic, you're imparting energy, you're putting energy into them. That energy is going to be released. Yeah, it's released as sound and it jumps up there. So the energy you push in is going to be where it goes to bump it up in the air. This ball and this big ball, think of them as planets. Or think of this one as Earth and this one as an asteroid. If I drop them from here, what happens?
That one first.
Right, a couple of things. They go down the way first, they don't go up like the helium balloon. Why do they go down?
Because they've got oxygen.
Not too much to do with oxygen.
They're trying to work against gravity.
Well, they're not. Gravity is pulling them, right? You're right, gravity. Gravity is the thing that enables us all to stick to the planet. Otherwise, we'd all float off like the helium balloon. That's why the astronauts, you see them when they were walking on the moon, they can take massive big steps. Because the gravity, the force of gravity on the moon is a lot less than it is here on Earth. Gravity helps us stick to the planet. And everything, Isaac Newton found it was an apple, everything drops down to the ground. Now if you watch really carefully, the big ball is heavier, so it drops with more energy. When I've got it in my hand, it's called potential energy. When I release them, gravity forces them down. The big ball is heavier, so it bounces higher, so more energy. You watch what happens each bounce gets less higher each time until eventually it'll finish on the ground. Because when it hits the ground, it loses energy. You hear the sound it makes, that's it losing energy. Every bounce loses a little bit more energy until they're left on the ground. However, the big ball bounces higher than the small ball. If I put the two together and let them go, you watch what happens. Right? Good catch. Right? Let's go back in. So, you drop it. What is happening? Two things. The energy is being transferred from the big ball to the small ball, so it's suddenly got much more energy and it shoots off. And the other thing, if you're watching, thank you, if you're watching really carefully, is the big ball doesn't bounce as high. Right? That's what would happen if an asteroid hit into Earth. Massive release of energy. It would be a bigger explosion than a hydrogen bomb. So the astronauts and people working at NASA and that are always tracking asteroids to make sure they're going to miss Earth. When they come flying through, they're not going to hit into it and cause us a disaster. Right. This is where I start to worry a little bit. 2 eggs. Raw egg and a boiled egg. Now, can I remember which one was which? Right? How can you tell between a raw egg and a boiled egg?
Boiled eggs darker.
No. Without breaking them, I mean, how can you tell? Watch this. What you can do is you can spin them. Right? So you take your 2 eggs, you spin them, and you stop them from spinning. Right? Spin them, stop them from spinning. One of them continues to spin. This one rolls, but that one continues to spin. Right? So spin them again, stop them. This one keeps going round. So this one is what, the boiled or the raw?
Raw.
The raw. Right? The raw one keeps spinning. Why? Inside it, you've got white and you've got yolk, which are semi-liquid. So even though I stop it like that, right? The white and the yolk still keep spinning on the inside, which cause it to spin round. This one is just like one solid object. So when I spin it, stop it, it stops. Spin it, stop it, that one keeps going. And if I've got that right, this is the boiled egg. Correct?
Yeah.
Ooh, you're right, that was the boiled egg, that was lucky. Any volunteers for this one? Not at all. Right. Right, this one is the old conjurer trick. I'm sure you've seen this done before. If I manage this one, I want a round of applause. What we've got are 3 glasses, right? 3 tubes and 3 cream eggs. What's stopping the cream eggs from falling into the glasses just now? This plastic in between. Normally, gravity would be pulling them down the way into the bottle, into the glasses. This plastic is what's stopping them. What I'm trying to do is I'm going to try and knock it out quickly so that the eggs fall down into the glasses. Right?
Yeah.
And as I say, it sometimes works, sometimes doesn't work. So we'll see. Right? 1, 2, 3. Cream eggs is because we don't often always get it right. So real eggs will be going everywhere. Right? But if you remove that tray, you knock it out, you're removing friction. I'm applying a force to remove the tray, causing the eggs to drop down into the beakers. This one here, beaker of water, right? Just put some colouring in it so you can see it. And there's no plastic or anything on it. If I do that, you see the drips, right? Who thinks I can turn it upside down without spilling the juice? You've got more confidence than I have. Right, Ashot's getting away out the road anyways. Right, what I'm going to do is I'm going to try to turn it upside down without spilling the juice. Right? So try to get the centre properly first. I'm going to do it over here, nice space in case we have a spill. Right, what I'm going to do is I'm going to spin it round. Now you watch when I'm spinning it, at some stages the beaker will be sitting upside down here and the juice won't be falling out. Right? Yes? There you go. The thing that tries to pull the water out is gravity. Obviously, if it's upside down, normally gravity would pull all the water out and spill all over the floor. But when you spin something round in a circle like that, there's another force. It's called centrifugal and centripetal force. And centripetal force forces the weight of the beaker against the tray. Even when it's upside down, it still gets a force up the weight, and that stops it from spinning out. So you can spin it round without actually losing any of the stuff out of your beaker. I'd love to see it works every time, but we've had a few spills on our travels. Right, these next set of experiments I'm going to explain are ones you do at home. You can show your mums and dads or brothers and sisters. Quite easy things to do. This first one, all you need is a blank sheet of paper. You need somebody to help you. Your hands up first, again on the back row, the middle. You
roll up the paper and then...
That's exactly what we're going to do. Take your piece of paper, roll it up like that to form a tube. Right? And what we're going to do, just come, it's right, just watch the cables and everything. What's your name? Caitlin, right, Caitlin. What we're going to do is you're going to hold it in your hand like that and you're going to put it up against one eye. You're going to look at somebody in the back row there. Right? Your other hand you're going to bring across like this and touch the tube. Right? And you're then going to tell the class what you can see. Right? So keep both eyes open. Hold that in tight to your eye. Keep both eyes open though. Open. And then bring this one up to there. And you see, there's the tube goes. Can't be going through your hand, surely. It looks like that, doesn't it? Yeah? What it does is what we call an optical illusion. Normally when you look at something, you've got two eyes, each one sees a different image. They send a signal to your brain, and your brain merges the two images together. Right? We have what's called binocular vision, two eyes. When you put this up against one eye, all this eye can see is out the end of the tube. This eye, however, can see everything around that side. Peripheral vision, we call it. When you put the two together, your brain gets confused. And it tries to merge the two images. So it makes it look as if the tube is going right through the centre of your hand. That's it. Yeah. So that's one you can try quite easily when you get home. You just need a blank sheet of paper. Okay, a round of applause for Caitlin. It's quite interesting in space. If we look at somebody, say this whole lecture theatre was full, and I'm looking at somebody in the back row, they'd look tiny, wouldn't they? But I know, my brain knows they're a long distance away, and that's what makes them look tiny. It's called perspective. If you're an astronaut in space, however, you're looking out at stars or other planets that are millions or hundreds of thousands of miles or millions of miles away, so you can't judge how far they are away. Our brain is quite good at judging things. I know if Ashok's sitting in the front row, he looks that size. If Ashok's sitting in the back row, he looks that size. But he's actually 6 foot. And he's 6 foot whether he's sitting in the front row or the back row. But in space, you can't judge distance. Your eyes have difficulty. Right? This one I call the black hole. I think I showed you this the first day I was down at opening the space school. All you need is a black sheet of black paper, works better, a 1p piece and a 2p piece. You put the penny down, draw around it like that, and then you cut that hole out. Get your mum or dad to do it. The 1p piece can drop just through the hole, just and no more, right? The 2p piece is much bigger, so it can't possibly go through the hole, right? But it can if you take the paper, bend it in half through the hole like that, open it up again and drop your 2p piece in, and then very, very gently ease it up though. Right? Now the hole is still the same hole. I haven't topped the paper at all. But by moving up like that, you convert something which is normally in 2 dimensions, you make it into 3 dimensions. When I make it into 3 dimensions, it makes the whole bigger. So suddenly, the 2-pence piece, which is now around here, I'm going to get it. The 2-pence piece is now bigger and is consequently able to go through a hole that otherwise you think it should never be able to go through. Right? It's not magic, it's science, it's physics. Right, can you help her for this one? Right, you was the first hand at this stage, yeah? Right? This one you need 3 pencils. Nice sharp points on them. You get worried? Nice sharp points, no? No? Right? Take them together with a bit of sellotape. Right, Matthew's going to help me. Stand and hold one finger up there like that. No, your index finger. No, this one. Right? Okay. What I'm going to do is I'm going to touch Matthew's finger with 1 pencil like that, or with 2 pencils like that. And you're going to shout out from the class whether it's 1 pencil or 2 pencils. But you're going to get eyes shut. Alright? So, is it 1 pencil or 2 pencils? Sorry. 1 pencil or 2 pencils? 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 Right, open your eyes. Everyone right. Okay, you got all of them right. Even with your eyes shut, Matthew could still tell whether I was touching his finger with 1 pencil or 2 pencils. Can you pull your sleeve up to about the elbow? This time we're going to do the same, but this time we're going to touch that part of your arm. Right, so keep your eyes shut, same again. Nice big loud voice. 1 pencil or 2 pencils?
2.
1 pencil or 2 pencils? 1 pencil or 2 pencils?
2.
1 pencil or 2 pencils?
1.
1 pencil or 2 pencils?
2.
Right? You got about half of them right that time. So why is it on his fingertip he can get them all right, and up here you can only get about half of them right? And if you're guessing, you would get half of them right anyway.
Because the nerves in your fingers are...
Exactly. Nerves. In our body, nerves are the things that enable us to feel, touch, sense different senses. You can feel hot, cold, pain through your nerves. And the nerves all run up your arms to your spine, and up your spine to your brain. And your brain interprets. So even with his eyes shut, his brain still knows by feel, by the nerves, whether it's 1 pencil or 2 pencils. This part of your arm, you don't have as many nerve endings. Have you ever given yourself a paper cut? How sore was it? Really sore, isn't it? Now take it from me, nobody has ever died from a paper cut. It's not a serious injury, but it's sore because you're cut through some of these nerve endings. And the reason we have lots of nerve endings on our fingertips is because we're always picking up tiny little things, and twiddling little dials, tying your shoelaces, and you need sense, you need feeling. Imagine what an astronaut's like in space when he's got these huge big suits on to keep his air pressure up, big gloves, he's got no feeling at all. He or she has got no feeling in their fingertip. It makes simple everyday tasks very, very difficult. Okay, a round of applause for Matthew. Right, we need 2 people this time. Right, your hands up first. What about right at the back? And right. Right, what's your name? Sorry? Matt. Right, Matt, you look strong. What's your name? Stephanie. Right, Mark and Stephanie. What I've got here is a potato with 2 straws. Right, Mark, you look strong. I want you to take that potato, take the other hand of the straw, and I want you to push the straw as far in as you can. Well, you said you were strong, Mark. Right, try forcing it in. No. Right. Mark can't get the straw into the potato at all. Stephanie, you take this straw, you come around this side, so we can see. Right, let go. You must have big muscles, Stephanie, compared to, you know? See how far Stephanie got it to go into the potato. Yet Mark couldn't get it in. The reason is because I told Stephanie how to do it. If you take it and you try to force it like that, even I can only get it in about that much. If, however, I take the potato and I do it from a distance like that, it goes in. It's a long way. The reason is I am giving it extra force, but they call that force something. You know what they call it?
If you're driving your car and you give it extra pedal, what do they call it? What pedal do you hit in the car to get it go faster? Acceleration, that's right. By moving the straw fast through the air like that, you're giving an acceleration which gives it more energy, more power, and it's able to go into the straw. Okay, thank you. Right, you want to come out for this one? Yep. Just because you're in front there. I've got a nice easy job for you. Right? I've got a sharp needle here, very sharp point on it. And I'm going to get, what's your name? Ishmael, to put it into the blue without bursting the blue. Right through the blue without bursting. Without bursting, eh? Right? I think that's impossible. Looks impossible, doesn't it? If you take the needle and instead of going through the balloon sideways, you go in near where it's been tied and out hopefully the other end where it's a bit loose. Hopefully I can put this right through the balloon without bursting. Hopefully. Sometimes it works, sometimes it doesn't. So I take it here and I work it backwards and forwards, go in. Right. Now getting in's easy, getting out the other end's a bit more difficult usually. The problem is you can't see where I would do it. And I twist it gently. There we go. Right through from one side to the other side without bursting the balloon. If I do that, however, burst right away. Right? Okay, thank you. The reason you can do that is at that point, at the bottom end, near here, the top end up the very end there, the rubber isn't stretched as much. And it's when the rubber is stretched, when you blow up a balloon, the gas fills up like we saw earlier, expands it. If it's fully expanded, then the skewer will burst it. If you go in through here, it's what's called surface tension. The contact between the metal skewer and the balloon is not so great, and it sticks to the metal skewer. Keeps the air trapped inside the balloon. Right, we're going to move on now to something different. We're going to talk about electricity and electrics. Right, we all know if we switch the lights on, we've got power. The reason is electricity moves in circuits, right? What I've got here is a little device called a glow bulb, right? You can see on the back of it there are two electrodes. If I touch one of them, nothing happens. If I touch both of them with one hand, right, the light comes on and makes this sound. The reason being, the electricity or the electrical circuit is completed. So the electricity is going from this metal through my finger, round through my hand, and when I touch the other electrode, it makes a circuit. If I take it off, take either of them off, it stops. Same if I do it one finger from here and one finger from this hand. The electricity is going up my arm, across my chest, down the other arm, back to there. Now the reason electricity passes through your body is your body is made up, 80% of it is water. Right? We're made of water. So the water conducts electricity. So I touch that. We'll try something. Everybody in the front row hold hands. Or maybe not everybody, right? You four people, right? You hold my hand, right? I'm going to touch that one, and you touch that other one there. The electricity is going through 5 of us to make the circuit. Hold hands again. Yeah, as soon as you take your finger away and break the circuit, it stops.
I bet if one of us did it.
You try it. Broke the circuit. Yeah, electrical energy, electrons are going all the way through all of us, back round to here. Again, one last time. Take your hand away. Break the electrical circuit. Right? That's electricity. Now, this device here is called a capacitor. It looks like a big battery. It's not, it's called a capacitor. What it does is it stores up electrical energy. On the jig here, I've got 5 batteries. When I put that onto there, the electricity from all 5 batteries is stored up in the capacitor. Right? Now, if I put these metal probes on just to protect the end of the capacitor, you watch what happens when I touch this piece of tin foil. Now, before I do this, the The electrical energy from here is going to be converted into 3 types of energy. I want you to tell me them all. Are you watching? Right, so the electrical energy was released as 3 types. What 3 types? Sorry? Negative. No. Electrical energy converted to 3 other types of energy.
Heat energy, light energy, and sound.
That's right. Heat. Can you see the holes it's made? If I do that. Put the holes in here. Light energy is the sparks, and sound you hear it crackling. Where in nature does that happen? Where you get a big build-up of electrical energy and then a sudden rapid release. Right? Lightning, that's right. Build it. It was happening in the football last night. I watched it on TV. We had a big lightning storm, and you see the flashes of lightning. That is electrical energy from the sky being released. Lightning is the light, thunder is the sound. And if you get hit with a lightning bolt, believe me, you'll feel the heat. Right? That's why golfers, if they're playing golf and it comes on thunder and lightning, they stop right away. The reason being, if you're standing with a piece of metal in your hand, and there's lightning, where's the lightning going to go to? Right to that piece of metal. So they put the clubs away, they all stop. The hooter goes, they take them all off the course. Right, I'm going to do the same again. And I need Ashok to come and give me a hand with this. Ashok did bargain for this. Right, you hold that. And then you both hands. Right, what I'll do is I'll put this back onto the jig again to charge it up again. So your red light, when it goes off, it's properly charged. Right, so we've now stored up electrical energy in here again. What do you think will happen when I touch it to this can of Tango? Burst open.
Yeah.
You watch then carefully. I'll try to do it carefully up here. Nothing. It's a bit odd. Bit of a disappointment. Why did nothing happen?
Because the can's made of aluminium.
No, but this is made out of aluminium as well. And aluminium is a metal, and metals conduct the electricity, so does water, so it goes through our body.
Is it because you want to pointy bits?
No, I held it, you just need to trust me, I held it. What is on the surface of the can?
Oh, colour.
Paint, that's right, paint film. Paint is made of plastic. Plastic doesn't conduct the electricity, so it doesn't go through the plastic. However, the bottom of the can hasn't got any plastic paint on it. You watch what happens. Right? Right? Drop it down in there. It shoots up in there. The last school I was at, I went 20 yards across, got all my front of my face, my glasses. The students do it. Right? So the electricity goes through metal and allows it to discharge. Right? This device here is called a Van de Graaff generator. This is just a very small one. It's just to let you see the principle of how it works. Word of warning. This is plugged into the wall over there. The electricity that comes out the wall is 240 volts. What would happen to you if you touched 240 volts? That's right, you get electrocuted, it kill you. So you never play around with electricity, okay? If something happens in my house with the electric, something goes wrong, I get an electrician to come in, because he or she knows what they're doing, and I'm not absolutely sure. Although this device is plugged into the mains electric, all that does is it runs this rubber band. The rubber band goes round and round and round on the inside. That rubber band is creating what we call static electricity. And it's creating the static electricity over the surface of that dome. If I put my arm near it, you might be able to see the hairs of my arm get attracted to the dome. And if I go too near, spark jumps across my hand. It doesn't hurt a lot, but it gives you a little shock. You see the spark jumping across if I do that? You see them? The static electricity that's built up on here jumping across to this metal dome. A bit like a mini lightning storm. Right? That's called static, and there's always some charge left at the end. You've always got to make sure you do it one last time to take the static away. Now, I'm sure you've maybe seen this happen with balloons, right? Somebody rubs it and they move their hair around, or it rubs it and sticks on the wall. If you could take an empty juice can, I should have had this, forgot to set this one up. If you take a can, try to see it here. If I rub this on here, next to the mic. See it make the can move? No, it's just the air inside, carbon dioxide. It's the rubber of the balloon. When you rub the rubber on here, it creates an static electricity charge on the surface. Because this is made of metal, it will attract it towards the charge, pull it along the cable. Okay. Right, we're just about finished. I've got one last thing to do as part of the show. We're good time, that's not too bad. This one's called the foaming cylinder. Can you remember way back at the start, the silver mirror had to work it really hard to make it happen. Put a lot of energy into a reaction. Some reactions are the opposite. Some give off energy. This one here gives off energy in the form of light when you mix the chemicals together. This one here is called the foaming cylinder. You'll see why. Put the first chemical in, it's called potassium iodide. Down at the bottom. You all know what this is because this is fairy washing up liquid. I'm sure you all do the dishes for your mum and dad, don't you?
Yeah, I get paid for this.
Oh, you get paid for it? Oh, that's terrible. Right. Things have changed since my day. I never ever got paid for doing the dishes. A wee bit more than I think. Let's drop it. Now, this last chemical that we put in is called hydrogen peroxide. I wonder if any of the teachers can tell me what to use hydrogen peroxide for. Bleaches your hair, right? I'm ashamed to say my 16-year-old son used to have beautiful white streaks in his hair that the barber put in using this stuff, hydrogen peroxide. But you watch what happens when I put it into here. It's called the foaming cylinder. Here's why. Now, if we're really lucky, it'll stay inside the basin. Right? Can you see steam coming off from here? See the steam? It's actually quite hot. Now that's about enough. Whoa! Yes, see the steam? Very warm. That's called the foaming cylinder. And that's energy being released. It's very important when they're working in space and chemicals that can react to give off energy. Because they're very often short of energy supplies in space. Now hopefully you've enjoyed the show. Hopefully I've managed to surprise you once or twice. What I'd like to finish off by asking you is, all the developments in science technology is what we use in every aspect of our daily life, not just for space travel or space exploration. When I was about your age, I sat and we watched, with my father, we watched American astronauts walking on the surface of the moon. Now for my father that was amazing, because when he was your age, he used to see at the cinema people going to Mars and going to the moon in a spaceship, and that was fantasy. Something that could never ever happen. Yet here he was watching it for real happening within his lifetime. So what I want you all to do, just for a second, is think of something that you believe is impossible. Just think of it. Don't say it out loud, just think of it. Because some of the things that you're thinking about will happen by the time you're my age. Right? And it might be cars that don't go on the road but they float in the air. It might be people living till they're 150 years old. I think that'll happen in the next 100 years. Because of the developments that are happening in medicine. My first mobile phone was a thing about that size. A huge bit, it couldn't fit in your pocket. And that was only about 50 years ago. My mobile phone now is about this size, about that thick, and it takes photographs and it can link it to anywhere in the world by the internet. All that has happened in 15 years because of science and technology. And I'd love to believe that one of you out there becomes a future astronaut. But what I'm certain of is that some of you out there will become the future scientists in Dundee and Tayside, making all these wonderful new discoveries that allow science and technology to develop in the future. Hope you've enjoyed the show. Don't give away any of the clues to the other group. Okay? Right, thank you very much.